Our team at Anaflash has developed an AI microcontroller with embedded flash memory. We will discuss why we designed it and how it benefits the edge AI application. This is the outline we're gonna present today. I will start with a brief background before explaining our design. In particular, I will cover the near-memory computing unit, which I will refer to as NMCU, and the word line driver, which I will refer to as WL driver for embedded flash. Finally, I will present the silicon test result and conclude the presentation. To power the intelligent edge, AI is indispensable. However, two key challenges stand in the way: power efficiency and cost. For example, customers want AI models with more computations and higher accuracy, with minimizing the need for frequent battery changes. Every intelligent edge device requires non-volatile memory to store AI parameters and a high-performance yet efficient AI processor. Our technology delivers both, enabling smarter, more sustainable edge computing. Traditional non-volatile memory, such as STT-MRAM, demands extra processing steps, increasing cost while offering only 1 bit per cell capacity. Our solution overcomes these limitations with a seamless, comfortable embedded flash memory that requires no additional masks and scales efficiently, delivering a high efficient and high cost efficient and high performance alternative. Let's go on to the architecture of microcontroller. In most edge AI applications, memory bottlenecks are more common than computing bottlenecks. For example, HBM is one solution to address this issue, but it is costly due to the use of advanced packaging technology, including GPUs and memory chips in a single chip to enhance their high-speed interface. To tackle the challenge, we present an AI microcontroller with zero standby power weight memory featuring 4 bit per cell embedded flash technology, which is seamlessly integrated with an accumulated calculators. This is why we call it near-memory computing unit. A key benefit of this architecture is tightly coupled wide I/O interface between the NMCU and flash memory on a single chip, enabling efficient AI processing. Additionally, since flash is a non-volatile memory, there is no need to fetch data from external memory after booting or waking up from deep sleep. This feature makes it a strong candidate for many edge AI solutions. We implemented all of this using a standard logic process without any additional steps. Next, let's take a closer look at how the NMCU is operating. The NMCU, based on embedded flash memory, consists of three main components. First, the control logic manages weight addresses in the embedded flash memory and regulates the input-output buffer flow, allowing mega operations to be executed in a single instruction without CPU intervention during processing. Second, 16 processing elements enhance parallel computations by sharing weights transmitted from each bank of the 8 embedded flash macros through a high bandwidth I/O interface. Finally, the last stage block quantizes the 32-bit MEG operations result into 8-bit activation values to reduce the memory size. The control logic is responsible for controlling the flow of ML operations. It automatically manages the addresses of the embedded flash where the weight parameters are stored, as well as the initiation of read operations, thereby minimizing CPU intervention during ML operations. Additionally, it allows selecting input from the input buffer and ping-pong buffer and includes logic for storing the final activation values from the quantization logic into the ping-pong buffer. Here is the P clusters that consist of 16 vector processors called process elements. Each P is implemented with digital logic based on an adder tree and can perform 8x1 vector operations in a single cycle. To support partial sum operations, each P includes a 32-bit accumulation buffer. The quantization logic is a hardware logic designed to quantize 32-bit computation result of the P cluster into 8-bit format. It supports the rel activation function along with 32-bit scale and bias, and it can perform shift operations to extract computation result in 8-bit format. By combining the 32-bit scale and shift operations, fixed point arithmetic can be implemented. This is how the operations of each block so far are represented in the time domain. First, after transmitting the input data to the buffer, the computation begins. At this point, the weight addresses are sent to each bank of the embedded flash where the weight data is stored. After 30 cycles, the data reaches the processing element. Since the MEG operations start only when the required weight data, the processing element does not begin computations during the initial 30 cycles needed for weight fetching. However, given that the program times of embedded flash memory is significantly longer than its read time, making it read-only during inference. We designed the system so that if the same address has been fetched, the MEG operations can start immediately. The logic for the MEG unit has been optimized to do complete computations within 28 cycles, excluding the 1 cycle needed for quantization and one another cycle needed for write-back from the 30 cycles for weight fetching. In this study, the logic was designed to perform 128 MEG operations over 16 cycles. To minimize the memory movement of the input data, we introduced the ping-pong buffer. To start DNN model layer 1 calculation, the input buffer is used for MEG operation, and the output value is written back to a ping-pong buffer A. The next step, when performing MEG operations using the ping-pong buffer, the NMCU automatically considers the data from the buffer where the previous result was written back as new input data and sends it to the processing element. For layers with input sizes that do not exceed the ping-pong buffer size, computation can begin immediately without additional data transfers, enabling efficient execution. For next layer calculation, ping-pong buffer connections are changed. This makes it possible to continue make operations without stop. I will talk about overstress-free WL driver circuit developed for QLC embedded flash technology. Conventional double driver circuit published in JSCC 2023 developed for embedded flash has NMOS only path to charge from VRD to WL. Because of the voltage drop and body effect of the NMOS only path, the verified read level for state S15 among 16 QLC embedded flash cell status has to be much less than VDDH. This results in limited embedded flash cell margin. To address this issue, we propose an overstress-free WL driver specifically developed for QLC embedded flash. Differently from the conventional WL driver circuit, we have separate boosted supply lines such as VPS 1234 and VPS 123 lines. Also, PMOS charging circuit from VRD has been added to extend S15 verified read reference level up to VDDH. Different level of VPS and VPP are generated by standard logic computable high voltage generator separately. Now we are going to check the experimental result. Here is the die photograph of our design measuring 4 by 4.5 square millimeters and fabricated using Samsung Foundry's 28 nanometer standard logic process. It features 2 blocks of 4-bit per cell embedded flash to enhance the wide I/O interface. Additionally, a tightly coupled NMCU is positioned next to the flash to accelerate parallel computations, while RISC-V processor handles additional operations along with SRAM and other components. Compared to other works, this design features a unique 4-bit per cell non-volatile memory without processor overhead. This slide shows the measurement result of overstress-free WL driver circuit for QLE embedded flash. The measured waveforms show that the selected WLs, PWL and WWL lines switch well to the different VRD levels from 0.5 to 2.5 volt successfully. This is the retention measurement result of the fabricated microcontroller chip running AI inference task. Both MNIST and the deep autoencoder were tested. You can find it that the weight distribution according to the threshold voltage. For MNIST case, the inference accuracy shows over 95%. It achieves nearly same as software baseline. For deep autoencoder case, it achieves the same accuracy of software baseline as 0.878 AUC. We did a benchmark test by deep autoencoder model from TinyML. Our cycle-accurate simulate result shows better performance compared to other design. Let's go on to the summary. Embedded non-volatile memory is essential for smart edge device to reduce power consumptions. Conventional embedded non-volatile memory is expensive, while density is not good. So we propose an AI microcontroller with embedded flash, which is fabricated in 28 standard logic. Thank you for all support for this work.